IASU, that is our ISRO Inertial System Unit Trivandrum. So Dr. Sangeeta is a senior engineer working at Artificial Intelligence and Space Robotics Division, ISRO Inertial System Unit Trivandrum. And she is a postgraduate in Control Systems Engineering with first rank and a gold medal. Congratulations, Dr. Sangeeta. And she is a recipient of the General Electric Foundation Scholar Leader Award in 2019. And she was awarded for the promising academic talent and societal commitments for her contributions. And apart from this academic achievement, if we coming to the professional career, I know that she has significant contributions towards the development of the space robotics payloads for various ISRO missions at IASU. And she has immensely contributed to the design and development of electromechanical scanning systems for meteorological payloads of ISRO. She also has been part of the teams which successfully realized high accuracy incremental rotary encoders for space application, which was an initiative towards the indigenizations and self-reliance towards these Atmanirbhar Bharat missions of our government of India. With these short introductions, so let us welcome the first invited speaker, Dr. Sangeeta Chiar, and she will be talking on the humanoid robotics for space explorations. So the Sangeeta, over to you.
Thank you, sir. Shall I share my presentation now?
Yes.
Is my presentation visible?
Yeah, yes, it is visible. Yeah, please go ahead.
Yeah. Good afternoon, everyone. So today I'll be talking on humanoid robots for space exploration applications. At the outset, let me thank the organizers of the National Space Science Symposium for having given me an opportunity to present our work, which we are doing at ISRO Inertial Systems Unit as part of this presentation. So the outline of the presentation will be, we'll be just seeing the space technology trends in the current years and the future vision, the need and relevance of humanoids. What is the state of the art in terrestrial and space humanoids? What is the kind of humanoid that we are trying to develop? What must be achieved finally? What are the different technologies involved, the facilities required, a glimpse of them. And finally, I'll also be presenting on behalf of our team from ISRO Inertial Systems Unit, the excerpts of the experiments and the current status of development of the half humanoid at ISRO Inertial Systems Unit. Coming to the space technology trends, a global perspective. So this is basically the roadmap which has been taken from the global exploration roadmap generated by the International Space Exploration Coordination Group, of which India is also a part. So as you can see, we are moving from the Earth orbit to the moon, which is we have already moved forward to the moon and to the Mars, with the ultimate goal being developing human habitat on the Martian surface. That is getting a lot of impetus now in the recent years. It has only increased in the recent years. So basically, the major takeaway from this is that we'll have a number of, as you can see here, the deep space gateways and similar space outposts will be coming up in either the lunar orbit or the Martian orbits. And we'll also be having colonies, and we'll also be needing to build colonies for human habitation in all these interplanetary surfaces. So basically, it is pointing towards long duration missions and long exposure to space environment and interplanetary environment, which is not very conducive as the environment that we have on Earth. Now, what is the role of space robotics in all this, the current trend that the space technology is going to follow? There are two kinds of applications in which the space robots will be finding an application. One is the orbital robotics for near space or microgravity manipulation, and another is the planetary robotics for exploration missions. That is on the interplanetary surfaces. So for the orbital robotics, there are two kinds of applications that we're looking forward to. One is the on-orbit operations. So as we know, as the number of missions are increasing, more and more spacecrafts and capsules will be sent to outer space, and the debris is increasing day by day. So we have to reduce and reuse. So that again calls for servicing and repair and maintenance of the already existing satellites so they can be put to good use, as well as it also calls for the debris collection and removal. All these are areas in which space robots find a lot of application. Additionally, we'll also be using all these space robots for assembly tasks like on-orbit assembly of telescopes, antenna, etc. And coming to the intravehicular activities, IVA, we'll require astronaut assistants who can coexist and work with the astronauts. Then artificial intelligence enabled free flyers, which will support the astronaut for the experiments, and even companion robots. Coming to the planetary robotics, as I understood that there's already a session which is completed on the in-situ resource utilization on Moon and Mars. So from those presentations itself, there have been much evident that the robots do have a role to play in the planetary environment, as well as in different reconnaissance and field study required for establishing a habitat. So as seen from this figure, whatever is in the microgravity environment on orbit, there also robots have a role to play, as well as on the interplanetary surface. Now, these are different kinds of space robots, just to refresh the basic facts that you already is there in the public domain. So Canadarm is already there, Rockquist mission has already been flown to the ISS, and Gitei is another mission which was recently flown in 2021 October, and it demonstrated activities by a robotic arm on ISS. Then these are the class of space flying robots which have already there on ISS, including the Astro B. And we are also planning a small technology demonstration of a smart space robot, which is an AI-enabled microclass satellite, which will be also capable of, it's a flying robot capable of performing on-orbit operations as part of developmental activity in IASU. And we expect it to be flown sometime in the fag end of this year. The other kind of robots will be the rovers as well as the leg robotic assistants. So earlier, as we know, we have already come across a Spirit, Opportunity, Perseverance, and the rover classes have already been there on the interplanetary surfaces of Mars as well as Moon. But now the research is more oriented towards finding out if the legged locomotion will be much better in navigating the interplanetary terrain. So that is what you see here, the research going on in SpaceBok in ETH Zurich. And coming to the legged robot assistants and even the humanoids, the next class is the humanoids. The humanoids, as the name suggests, it can be as even a half humanoid or a full humanoid. Full humanoid will be having the lower body also, whereas a half humanoid will only be having the upper body, upper torso, the arms, hands, and the even a face or a vision system for the scene perception. So here what you see is Robonaut 2, which has already been flown on the ISS. The second one is the Valkyrie, which is touted to be exploring the Martian surface in the coming years, which is also a NASA robot. And here in this third picture, we are presenting the half humanoid Vyom Mitra, which the rendered model of the Vyom Mitra, which will be flying in the first unmanned, or rather in the crew module of the Gaganyaan mission. And as a vision, we have also projected a humanoid, a full-fledged humanoid with as a biped humanoid, which will be able to navigate in the interplanetary surface as well. So half humanoid can very well take care of the microgravity requirements within the constraints of a crew module, whereas a humanoid, full-fledged humanoid with either a leg pure, just biped legs, or quadruped legs, or even a leg with wheel concept can be useful in the interplanetary surfaces. Now here, I'll just show you the type of activities that is expected out of a humanoid, which is performing inside an ISS. This is a microgravity environment. So as you can see here, this is inside ISS. So basically manipulating the switches, doing some simple assembly tasks, all these are expected out of a humanoid performing inside in the microgravity environment, because this is just to show that these kind of cable operations are also, this is rolling just in action. So basically the kind of cable operation activities which may also be required in the long run. Now, why do we require a humanoid? So one of the reasons I have already put forth that it is one solution for multiple functionalities, because you can have a robotic arm, you can have a free flying robot which is artificially intelligent, you can have a rover which is able to manipulate different terrains. But all these activities combined together in one, that is what is contributed by a humanoid. That is, it can serve as an artificially intelligent or intelligent counterpart. It can work with dual robotic arms. It can also have some kind of locomotion or manipulation, locomotion ability, which will carry it towards, which will help it traverse different terrains. The most important of the favorable reasons why we need to go for a humanoid. It is basically suited for the human engineered environments. If you look around, we know that almost all the tools or the systems that we use are all engineered such that our human hands or arms are able to manipulate them. So it's much easier to retain the tools and systems as such. Even if you just look around, the room itself is designed for a human being, with a human being in view or in due consideration. So basically, this is what is the most attractive feature, that if you have a humanoid which is of anthropometric dimensions and proportions, which is look-alike of a human, then all these environments, tools, all these things we don't need to redevelop them, which is suited for a typical kind of any other typical kind of robotic system. It is a pinnacle of bio-inspired engineering. So why is this important? Bio-inspired engineering is basically looking to the biological principles to develop new engineering innovations. Sorry? Hello, am I audible?
Hello, there is a noise coming from other. Requesting LOC to kindly turn off the mics other than a speaker.
The mics are actually off, but
No, there is one. I can see that Sangeeta is Pujari. Yes. Yeah, now it's okay.
Okay.
Sangeeta, go ahead.
Yeah. So this is basically why we are looking at something like a bio-inspired engineering, because it will utilize the biological principles to develop new engineering innovations to achieve a higher level of efficiency than the conventional systems that we are developing. So this is possible only if we have some kind of matching or form, fit, and dimensions similar to the biological human being. It's an interdisciplinary system, so it will involve robotics, cognitive science, AI, and mechanical design. All these aspects have to coexist, and each has to be driven to its extreme ends so that it performs well. So it's basically an advancement of the technology as such. Then coming to the last point, the availability of intuitive training approaches. So with the advent of AI, we have lots of training. Training is possible, and it's basically mimicking the way the human beings are going to learn, or basically the human beings are learning. So the humanoid will be mimicking the same procedure. So here we don't have to create new training approaches or training methods or apparatus. In fact, something which is equivalent to a human being in form, fit, and function can easily learn from its human counterpart. Since this is particularly advantageous in this recent times when AI is coming up in a big way. So coming to the state of the art, terrestrial robots, I'm sure almost all of us are now familiar with the kinds of robots that is performing excellently well in the terrestrial environments, like the Atlas, which is executing marvelous locomotion, exhibiting marvelous locomotion capabilities, or the Ameka and the Sophia, which are excellent in their emoting of expressions, and different robots like HRP, 4C, etc., which is performing a very human-like locomotion or a gait. So we understand that there are a lot of terrestrial robots which are doing, in fact, they can be called the state of the art in this area. So what makes the space robots different from this kind of terrestrial robots? What are the challenges when we go for developing a space robot or a space humanoid kind of robot for when compared to the terrestrial ones? First itself, we know that it's microgravity. So any simple object that you can handle freely on Earth, that is not the condition with in space environments. There, the reaction dynamics, contact dynamics, vibration dynamics, all these play a role even in the manipulation activities, which are relatively simpler to carry out in the terrestrial environment. Then, as I said, we are looking for something like an anthropometric dimensions and form fit, which has to match the human being. So that has to be done within the constraints that the mechanical structure being designed should withstand all the launch vibrations and the other launch conditions, the launch acceleration and vibrations being felt. Then another additional thing is that when we choose each of the component, that should work for longer duration in this space environment. We are talking about planetary robotics. It has to be exposed to the extreme space environment for longer durations of time. So that puts a lot of constraint on the kind of components that we can choose. Then coming to the limited computational processing power, on terrestrial robots mainly have an advantage that most of them are run on cloud. that is all their AI and intelligence capabilities mostly are run on cloud or they're cloud supported. Whereas when we are trying to deploy a robot on board, we are really crunched with respect to the computation and the processing power. The next is the high efficiency, reliable operations. Once we fly to space, there is no way we can retrieve it. That is the same with any space system, but it is more prominent when it comes to a comparison between the terrestrial and the space robots. And we have to work with optimized power. There's no option that we can keep it continuously plugged in. So when it is asked to move into the open, it has to be carrying a battery or an optimized. So it has to work on optimized power. Then coming to the latency, on terrestrial robots, many of them can be commanded by the user. A teleoperation can be performed with minimum latency, but that is not the case with when it is going to be in space. The minimum latency for ISS to ground operation has been more than 5 seconds. Now, relevance of humanoids in near space operations. So now we'll come to the key points, that is inside IVA, in intravehicular activity. What is the typical activity that the humanoids will be performing? Manning of the space post, or it's rather not manning. It will be a robot which will be working 24/7, doing the health monitoring and the maintenance activities. It can perform monotonous daily operation activities, leaving crew time for other valuable experiments. Then coming to astronaut robot, collaborative experiments also can be there. It can even serve as an emergency rescue assistant for the robot astronauts. And it can even do long-term exposure to space environment, carry out different kinds of experiments. Another important factor is that it can provide psychological support for long duration missions. It is a very key point because man is a social being, and we require some kind of conversation or exchange of ideas and communication to keep us going. So that kind of psychological support and the feeling that somebody is there, a colleague is there, that kind of support also needs to be maintained and given by the robot. Coming to the EVA, as I had already discussed, this point is already discussed on refueling services, etc. So autonomous robot colleague within space stations or lunar gateway equipped for emergency response, health keeping of space modules, and experiment support. That is what we are typically looking at. So now what are the different kinds of activities which will be done by a space robot? So this is basically, I have taken the ISS demonstration of Gitai robotic arm. So you can see the speeds at which it is operating. It is now shown as into 30, so and into 100. So different kinds of assembly operations are being done by the space robot. And so this is basically providing a psychological support. This is also a video from the ISS where the Kirobo is the robot which is there, which is a conversational robot which can talk to the astronaut and be with him. It is an actual video from the ISS, JAXA Kibo module of the ISS. And the robot is called Kirobo. It cannot do any other activity, but it is able to talk with the astronaut and give some psychological assistance. So now this is the ILA robot, which is performing switch operations. So these are the kinds of operation that is expected out of a robot. It should monitor and do corrective action. Now, what is the relevance of these? Whatever I was talking about is about the microgravity robotics or near space robotics on orbit. Now, relevance of humanoid and planetary robotics. Planetary robotics is basically for the exploration missions on the interplanetary surfaces. The reconnaissance can be basically accomplished by a lander rover, but it is highly limited by the instruments that can be interfaced to their end effector. So when it comes to establishing a Martian colony, what we require, the next step of reconnaissance is required, which is field study. There we'll require in-depth analysis of the samples collected, and you'll require some kind of domain-specific intelligence to deduce from the samples collected. So we require a dexterous humanoid with human ranges of motion. And it can also serve to set up environment before the human being travels and be there. And third aspect is in situ resource utilization, which detailed a talk might have already happened. So in that, basically, from that perspective, you think an assistant who can verbally take orders, converse, perform assembly operations, walk around the site, serve as a companion, perform photography and data logging and retrieval support, all these with no fatigue. That's basically an asset to such long duration missions. Now, relevance to humanoids to space ground segment operation. There are many hazardous and dangerous activities which are necessary for even the ground operations of our ground segment operations. So that is like the hazardous test and operation for satellites and launch vehicles. then integration assembly activities in clean room. So there it is, the robot can be maintained in the clean room and it does not have any other issues that's associated with a human being there in a clean room. Alignment activities, pyro arming, disassembly of launch vehicle stages, or cleaning of the launch pad, hazard toxic chemical handling. All these aspects also a humanoid will be able to do, because we don't, this is where it is all important, that the aspect of humanoid, because we don't have to create new tools, we don't have to re-engineer environments, but it can seamlessly integrate into the environments in which human beings are working. So basically, what are we looking at? We are looking at a humanoid that will have anthropometric dimensions suitably configured to work in microgravity and exploration missions. It should operate in realistic, harsh, and hazardous unstructured environment. That's most important, unstructured environment. And demonstrate dexterous manipulation, provide cognitive assistance, even have robust, balanced, and energy efficient locomotion. Energy efficiency is a key factor. And the lower body that we can configure to suit the application environment. So even if it's a microgravity environment, we don't need specifically, legs offer no specific advantage, whereas for interplanetary surfaces, mobility is a must. And they should also display varied degrees of autonomy. So what are the key considerations when we go for finding out the configuration of a humanoid? Basically, the human being has about 230 degrees of freedom, but realizing so many to achieve all the dexterous list of activities will be having a tie with the complexity of realization, the computational load, etc. So all these things have to be kept in mind, and we have to map the human degrees of freedom to various capabilities, so that we have to assess the minimum number of degrees of freedom required to faithfully carry out the list of functions that we want. And this has to be tallied with the complexity of realization, computational load, actuator configuration, power demand, etc. The mass typically must be less than 100 kg, and power should be typically 1.5 kilowatt, which is estimated from the current, our experience in developing the half humanoid. Then coming to the dimensions, the anthropometric dimension is it is very evident from the dimensions of the human being, the human ranges of motion in each joint, and we can even have a prosthetic expressive face, which is a great advantage when it comes to cognitive support, which being provided. Coming to the locomotion specifications, typical values which have been achieved by the terrestrial robots have been put here. And even for the arm manipulation specifications, we have to list the number of activities which needs to be done, and mainly for support for IVA, it's manipulating switches or tools, and for providing emergency support, it can be the medical instruments and opening, closing valves, lids, etc. for certain kind of refueling or maintenance activities. So accuracy and repeatability, sub-millimeter level is required. The dexterity measure. So typically we say that if a hand is dexterous if it can execute 16 of the Katkowski grasp. And another important feature that we'll have to look for when you design when we decide the configuration of a robot is the compliant motion, because the robot is going to work in an environment where it will be co-working with the human being as well as its environment. So here the compliant motion says that coexistence is possible. There is no safety issues with the associated robot or the collaborative robot or the human being is a requirement. The payload capacity per arm and grasping force per hand, all these are also parameters which have to be decided based on the type of activity that is going to be carried out. Cognitive abilities, I had already mentioned them. Object detection, recognition. From the display, we have to read and report. We should be able to recognize the co-worker. Then cognizance for safe operating decisions. That is basically whether the next step that you're going to take is going to in any way harm the astronaut who's working along or the environment. All these things have to be inbuilt and incorporated. The natural language processing, it should be able to talk as well as respond through voice. And different kinds of autonomy is also required. If it works on a pure teleoperation, it's a robotic agent. If it's semi-autonomous with user commands, it will form a robotic assistant, and fully autonomous will be a robotic explorer. So this is basically a glimpse into the kind of multidisciplinary system that the humanoid is going to be. It's not just the actuators and sensors. In each of them, a lot of research has to go into so that we can, even in case of the type of gears, the transmission elements, the damping elements, the kind of actuators that is required, that is embedded or smart actuators which will be required. A lot of research needs to go into each of these areas to realize the humanoid. Now, we'll just see the key capabilities for both orbital and planetary operations. So as I was mentioning, energy efficient locomotion, because for a typical human gait, there is for one single gait to be completed, there is sustained periods of leg swing. So during sustained periods of operation, we should work with miniaturized actuators so as to meet the anthropometric dimensions and even the reduced thermal dissipations. The energetic performance of the robot can be significantly improved by incorporating passive dynamics and some kind of regenerative techniques, so that during the swing phase, we can regenerate the energy that is required during the foot stance phase. And this is mainly in considering the legged locomotion, but in other case also with the rover kind of locomotion, legged rovers also, we require the sensing and perception, traction mechanics, control navigation, etc. And all these needs to be performed on a naturally untouched environment when we're talking about the lunar or the Martian surfaces. Coming to dexterous manipulation, I had already covered this point, saying that grasping, it is not just enough to, the manipulation involves multiple different steps. Identify the object of interest, configure the body for optimal manipulation, grasping, the different types of how to grasp an object, that itself is a research area. And coming to the manipulation, we have to consider all these impact, reaction, as well as contact dynamics. Coming to the human-robot interaction, we should control the force and position in a non-conflicting way and develop a relation between the interaction force and the manipulator position, which is mainly the impedance control, which may be required for a smooth human-robot interaction. And enhanced level of interaction is basically by voice response and responding to voice queries. Tele operations, we had already touched this point that latency and bandwidth limitations needs to be overcome. And telepresence, which is very common in the terrestrial robots, that will require the operator to shift his presence to humanoid environment and start performing tasks based on the, and he'll be getting the feedback of the environment of the robot from the motion capture devices or the sensors in the robot. And network robotics, when we are talking about is through that is in situ resource utilization in planetary environments. It is not a single robot. There will be multiple robotic counterparts. They have to work in cooperation, coordination. So basically something like a wireless base station and a wireless communication also needs to be enabled between these robots. And coming to the another important aspect is autonomy and decision making. We need to have a detailed cognitive framework which will take the knowledge from, which will have a detailed knowledge base within itself and will be taking the inputs from the scene, deducing the decisions, or perceive the scene or understand the scene and take the decisions for a next step to move forward. And even by doing some kind of problem solving, just like how we humans do, and then give the actuation commands to the motor. They should always, this cognitive framework should also be responsible for resource allocation as well as resource management. There are different types of technologies which are involved in this development of a humanoid. That is the mechanical system, the structural design, the thermal design, so miniature mechanisms for multi-axis joints. Mainly it is, when compared to terrestrial robotics, wherein we find a lot of prosthetics, for the space application, we'll require special materials for these prosthetics. Coming to the actuators, we'll have to have energy efficient. These points have been touched upon. So we have to address the energy efficiency as well as the small form factor with embedded control electronics and the encoders. The transmission elements and the passive elements will have to be built in to achieve the compliance. Coming to the different kinds of a host of sensors will be required in addition to a terrestrial system and different other kinds of robots. What is additionally required in a humanoid, which will be more or less matching the human being, will be the artificial electromechanical skin, then e-nose for artificial olfaction, tactile sensors, then other interaction sensors like microphones and cameras, vision sensor systems. Vision systems itself play a real important role in scene perception. Then coming to the electronics and power, it is all the same for many other space systems, power management and 3D packaging and miniaturized electronics. That plays a most important role in achieving the dimensions. Coming to the modeling, control, design, scene modeling, etc. As I mentioned before, the whole body posture has to be maintained. So even with locomotion, we have to ensure that the whole body control or stability is maintained. Optimal grasp is generated. And additionally, the most important factor is the control design for zero G and reactionless manipulation. because basically if you are looking at microgravity movement or of the humanoid, let's say probably only the upper body is there and it is in motion, then we can say that it is basically like a reactionless manipulation that has to happen there, because the robotic arm will be moving and the reaction forces of the movement of the robotic arm will be felt on the base body. So that has to be either corrected actively or by some methods like the reactionless manipulation. And typically when we design and test in the ground environments, the same kind of gains, the tuning, the PID gains or the joint level gains will not be holding for the microgravity environments, because there basically the G effect is not there. So that has to be critically studied. Some kind of stiffness, whether it is contributed or damping is provided by the G effect, how that will not be reflecting in the microgravity environment, how the gains have to be tuned for this environment. All these things are various key points to be addressed in this development. Coming to the software framework and computing architecture, as we know, most of the terrestrial robots are working on edge computing devices, whereas when it comes to the space domain, we have to really choose an edge computing devices as well as on cloud support. Whereas when it comes to the humanoid realization for a space environment, we'll have to have custom-made real-time processor hardware with GPU capabilities to support the AI models and the AI framework. Teleoperation has been dealt with. Subsystem and integrated level testing. That is a very important point when we address the space robotic activities. As I said, the gravity compensation test setups, because microgravity operation, it's a multi-degree of freedom system, and how it operates in microgravity has to be studied in detail in ground itself before and confidence gain before flying it to space. Then coming to the motion capture system. Motion capture system is most important, and it's very effective in robot calibration methods, because this robot calibration is an essential activity which is importantly, it has to be performed, and how it is different for a terrestrial robot and a space robot, I just explained. For any industrial or terrestrial robot, what basically happens is, in whatever environment it is going to work, there it will be calibrated. And that is the most important way in which it is achieving the sub-millimeter accuracies or precision kind of numbers. Whereas for a space robot, during the launch itself, even micro-radian change variation, which can happen in the even one of the actuators can reflect as millimeter variations in the end effector locations. So that is so we don't have the luxury of calibrating in the environment which it is going to work. So we have to find out procedures for the on-orbit calibration of the robot. So all these motion capture system, etc., help us in achieving the robot calibration, basically. So this is certain of the test facilities which I'd like to show here. This is basically from the DLR locomotion test bed. This is the motion capture system which I was explaining. In the third figure, we are showing the planar air bearing. Here, as you can see, this is the actual the Vyomitra arm, half humanoid arm. The Vyomitra arm, which is undergoing microgravity testing at IIT Jodhpur. So the planar air bearing is being used for doing the microgravity testing. And here is a spherical air bearing test setup at IASU, where the attitude control loop testing of SSR is in progress. So that is also a kind of SSR or smart space robot, which I had already introduced. That is kind of a free flying robot with robotic arms, where the reactionless manipulation needs to be applied. So here we are showing the different kinds of test setup that will be required for developing space robots, space humanoids. So this is typically a vision that we could have. That is the way in which it should proceed, the development should proceed. In the initial attempt, we could address the concerns in the near space activities, wherein the dexterous manipulation, scene perception, HRI, and launch orbital environment. It should be designed for the launch and orbital environment. So half humanoid within the crew module will be a suitable example, or is the work towards this direction, near space IVE. The next could be the logical step should be going for exploration missions, wherein locomotion, cognizance, teleoperation, energy efficiency, and localization navigation. All these will be required for long duration experiments and field studies. And coming to advanced exploration missions like establishing a colony, in that case, where an in-situ resource utilization is required, there we could have an advanced humanoid. And this could as well have applications in the terrestrial domain also. So now I come to the point where I'll be giving details on the half humanoid or the Vyomitra, which we are developing for the Gaganyaan mission. The development is spearheaded by ISRO Inertial Systems Unit with active collaboration from Vikram Sarabhai Space Center, IAST academic institutions like IAST, IIT Jodhpur, as well as the Osmania University. So the half humanoid Vyomitra is a multi-degree of freedom robotic system suitable for operations within the crew module. It has been built and configured in a way which is suited or tailored to meet the requirements of the crew module and the workspace constraints there within. It is equipped with upper torso, arms, hand, neck, and an expressive prosthetic face, as you can see here. It has got hands, arms, neck, as well as an expressive prosthetic face. It is designed to withstand launch conditions, and it will autonomously function in orbit by learning from its environment. And this is also an example towards achieving a cognitive assistant for astronauts within the crew module, in addition to other manipulation capabilities that the Vyomitra has. So this is basically anthropomorphic, and it is a 35 DOF system. It's AI enabled, and the major, like, its mass is about 25 kg and the power is 60 watt.
Dr. Sangeeta, there's another 2 minutes.
Oh, so I'll just okay. So
Yes.
This is basically the what are the different features? The dexterous manipulation, the dual robotic arm task it is able to do. It can do different switch operations. The visual AI, it is able to recognize the objects of interest. Speech AI, it is able to engage in intelligent conversation, as well as AI-enabled expressive face is also there. It is working on a customized operation console. It also has the display reading capability and posture change mechanism. So here I'll show you the video of, it will be strapped. So basically, just like an astronaut is being strapped during the launch, the robot also has to be strapped during the launch. And it will attain an orbital posture once, an active posture when it starts the panel operation. So here I'll just show a few videos of testing in progress for Vyomitra. As you can see here, the Vyomitra 12 DOF head is on the vibration table and launch qualification is in progress. We are aiming at different arm manipulations. The hand gesture operation is being shown here, and it is greeting with Namaskar. So it is a coordinated activity of both the arms. We're also displaying the head nod and the neck movements and the switch panel operations that is typically required for operations within the crew module. The entire design is in-house, and currently all the launch qualification is in progress for the Vyomitra. So as you can see here, it is complex mechanical systems, precision mechanical systems, which has been assembled in such a way that it is meeting all the requirements of an anthropometric dimensions and common fit. So here I'll be showing the inner layer of prosthetics. So I was saying that's a prosthetic expressive face. It is the inner layer of prosthetics showing inserts for the attachment. Basically, we have facial action coding units for movement of to create the facial expressions. So here I'm showing the facial attachment points. As you can see, this is an inner layer of the prosthetics. So here I'll also be showing the video of the development progress of a prosthetic expressive face. You cannot miss the smile. Yes, that Vyomitra. So here basically we are also showing the lip sync to the text. Whatever speech is there, it is lip syncing. Now it will be overlaid with the prosthetics also. And typically, so what is the typical application of the half humanoid? As I said, switch operations are there and different other requirements there. Another key feature that the half humanoid or Vyomitra will be able to do is do experiment support. So we'll be having a space biology experiment as a collaboration activity between ISRO Inertial Systems Unit and IAST. So wherein we'll be performing the humanoid in-loop orbital plant experiment. That is basically a design of plant habitat and demonstration of seed germination and growth on board. For a typical mission duration, we'll be able to see the germination of seeds and growth on board. So what the role of the humanoid will be is the periodic water and nutrient delivery, as well as monitoring and reporting of progress of the experiments through vision feedback. So this is the main activity that we are substantiating, that experiment support can be performed by the humanoid, and in the long run, this can be expanded depending upon the requirements. So now I have introduced the half humanoid development also. So basically we brought into focus the kind of activities that is required for the humanoid development, the key features, and we also showed you how we have incorporated all of these features into the half humanoid Vyomitra, which is being developed for the activities inside the crew module. So thank you for this opportunity. I hope the inputs will be useful. And I take this opportunity to acknowledge Director ISRO Inertial Systems Unit, and also due credits for the humanoid design team at ISRO Inertial Systems and all our collaborating institutes as well. Thank you for giving this opportunity to represent the team and present the work here.
Thank you, Dr. Sangeeta. It is a very wonderful talk and very informative and exciting, because technology per se, humanoid robots are the future technology for space explorations, and it has a wide range of applications for space as well as terrestrial, as you have highlighted. And in the humanoid, the most actually determining parameter is the degrees of freedom. You have mentioned that the Vyomitra has achieved around 35 degrees of freedoms and 12 degrees of freedom in the head. So it has a very good. And if I remember correctly, human body, because basically the humanoid robots are the digital twins or replica of the human bodies. So human body is very complex systems. It is having around 230 degrees of freedom. And achieving this in terms of degrees of freedoms, bipedal location, dexterity, then anthropomorphic look is a really tough task, interdisciplinary. So hats off, great work to our IASU team, and all happened because of the constant support and exercises from our respected directors. I understand that. So we will have a very quick comment from Dr. Bikram Rana. Over to you, Dr. Rana.
Humanoid, our Vyomitra is mainly, as I was just pointing out, the microgravity and planetary robotics. So here, Vyomitra is mainly for the microgravity or orbital IVA kind of activity within the crew module.
Yes. Dr. Rana?
Okay. I would like to thank Dr. Sangeeta for such a nice and a very in-depth talk. Actually, she started from very basics of the robotics and went up to very complex systems like Vyomitra. So it was very exciting, and all the videos were very exciting to see all the actions and finally achieving this complex systems. This could be a game changer, especially in the space exploration. So I would just wish her best luck for her project, and again congratulate her. Thank you.
Thank you, sir.
Thank you, Dr. Sangeeta. So we thank you once again for your quite interesting and exciting talk. So please be with us. We have other presentations. Since we are running short of time, we are not taking up questions. So people can write questions in the chat box. We will actually help reaching to the speaker. So next presentation is from Dr. Stellan Peter Gori from TIFR, Tata Institute of Fundamental Research. So Dr. Stellan will be talking on the design and deployments of the medium volume aerostat to provide Wi-Fi communication at remote sites. So over to you, Dr. Stellan.
Good evening, sir. Am I audible?
Yeah. Yes, you are audible.
Yeah, one second. I'll just share it.
Yes, slide is seen.
Seen, sir?
Yes. Please go ahead.
Yes, okay. Good evening, sir. My name is Stellan Peter. I am working with TIFR for Balloon Facility, Hyderabad. So I belong to the balloon group, which basically does balloon design, balloon fabrication, and launch operations of zero pressure balloons and other balloons as well. So today I'll be presenting about the design, fabrication, and deployment of medium volume aerostats to provide Wi-Fi communication at remote sites. Before that, I'll just give an overview of scientific ballooning. I have categorized the balloons which we make at balloon facility into 5 types. First one are zero pressure balloons, which carry heavy payloads up to 2000 kg, and they can reach altitudes of 43 kilometers maximum. The applications mainly include astronomy, atmospheric science activities, engineering payloads, and others as well. So recently we have developed a large volume aerostat which is capable of carrying 4 ton up to 10 kilometers. So the balloon is also successfully flown with 4 ton. Coming to next one, these are called sounding balloons. These carry light payloads up to 5 kg and can reach 43 kilometers height. They are basically used for atmospheric science and wind probing flights. Coming to other category, these are called special balloons. These balloons are exclusively made for URSC Bangalore to conduct zero gravity tests for their payloads. So in a controlled environment. So we have developed two types of balloons in this category, namely sphere shaped and orbit spiral shaped. The main difference I'll explain in the next slide. Next are stratospheric balloons. These carry light payloads up to 10 kg payload, and they can reach as high as 48 kilometers. So they are basically used for upper mass science activities. Coming to the last category, these are called tethered balloons. So these balloons are tethered with the use of help of winch. There are two types of balloons in this category. Those are natural shaped balloons for heavy payloads, and they can reach up to 1 kilometer altitude. And another is aerostats for light payloads, and they can also reach 1 kilometer. So basically, these are used for payload fabrication and boundary layer studies. So my topic will be based on this aerostats design. Before that, I'll just explain about how a zero pressure balloon is designed. So the main inputs for a zero pressure balloon design is like the payload weight and altitude requirement. So you can see some basic components of a zero pressure balloon. Besides the envelope, there are something called as side escape tubes, which vent out gas after reaching the floating altitudes. And these are top and bottom end fittings just to close the balloon from top and bottom. And also there is a disturb device. There is a button kind of thing which is attached to the near top. Then there is a rope which goes from the top to the bottom and to the payload. So after the experiment is over, the balloon is destroyed using this disturb device button. Then we are also having something called as inflation tubes to inflate the gas inside the balloon. Coming to the fabrication process, it is a very tedious task to fabricate a balloon. Like coming from, we need to have some balloon film selection for the required payload and to reach an required altitude. Then accordingly, we will design the balloon. Then we will prepare the marking sheet for the balloon required. Then we will align all the sections required to see each and every section for the balloon to make up. Then after that, we will attach all the instruments which I have spoken earlier. Coming to special balloons, as I have mentioned, so these are exclusively made for URSC. One is sphere and another is orbit spiral shaped. Sphere balloons are used to lift their payloads just above the ground, so that they can have simulated zero gravity condition to test their payloads. So what happened is like there is a height constraint within these limits. So whenever there is an increase in payload, the sphere balloons cannot take up this heavy payload. So what we have done is we have designed orbit spiral shaped balloons so that the height can be decreased and the volume can be increased. So in this way, we have developed two types of balloons, and we have successfully designed, fabricated, and supplied these balloons to URSC Bangalore. You can see some of the photographs of the antenna deployment and the Mars rover and other instruments as well with the use of our balloons. Coming to tethered balloons, these are natural shaped balloons. These balloons volumes range up to 275 cubic meter, and the payload weight range up to 150 kg. So they can reach an altitude of 1 kilometer. The potential users of this are mainly NARL. So, and we have also provided this facility to Tata Services to test their payload before deployment. Coming to the available aerostats at balloon facility, we have three kinds of aerostats. One is 3.3 cubic meter aerostat, then 9.9 cubic meter aerostat, then 20 cubic meter aerostat. This 9.9 cubic meter aerostat was designed during 1970s by IISc Bangalore professor. So I'll just give you the configuration of these balloons, aerostats. The 3.3 cubic meter aerostat can carry a maximum payload of 1 kg and can reach 350 meters above ground level. And 9.9 cubic meter, this can carry 3 kg payload and can reach up to 1 kilometer altitude. Then I have designed 20 cubic meter aerostat based on this 9.9 cubic meter aerostat volume design. This can carry a maximum payload of 7 kg, and with 3.5 to 4 kg, it can reach 1 kilometer altitude. So all these balloons are made with linear low density polyethylene film with 75 microns thickness film. Coming to the design of this 20 cubic meter aerostat, as I said, the 9.9 cubic meter aerostat was designed in early 1970s. So because to increase the payload capacity, we have designed 20 cubic meter aerostat. The design looks simple. It is more of a GNVR shape. That is GNVR is a professor from IIC Bangalore. The main design concept lies is like the nose shape is a hemisphere shape, and the remaining there are up to tail shape. There are concluding cylinders with it, and you can see there is a material that is volume that is inside film that is presented. Coming to aerostat fabrication, this process involves a very typical task. From initially selecting the material, then we need to make a template so that the total shape of the fabric aerostat can be made. Then again, we have to align all the sections in that one, and we need to cut along the shape. Then we need to do sealing. Then we need to go for fins fabrication. These are like inflatable fins. So mostly inflatable fins, the advantage is like we can have volume inside inflatable fins so that we can have more payload capacity. And another is like then we have to fabricate the fins, and we have to attach the fins to the main hull section. Then we need to have confluence patches. Confluence patches are patches which are basically used to fix the patches at the parts of the balloon so that and they can reach up to the payload weight. And there are ropes attached to these confluence patches. Then we need to test the aerostat after fabrication so that there is no leakage or anything is there. Then after that, we need to make some angle of attack adjustment for the aerostat to go and to have a smooth airflow. Coming to deployment requirements, there must be some things that we need to take care of, like a winch, which can be a electrically operated one, then or a manually operated one. Again, we need to have a lift gas to inflate the aerostat. Then we need to have some launch area. Small area is required, but we need to have it. And again, we need to have some cloth so that initially before inflation, we can smoothly put the aerostat. And after inflation, completing the process, for deflation also, we need to use the cloth so that we can neatly fold the aerostat and keep it in a good condition. Coming to past aerostat deployments, so we have besides deployments of aerostats at balloon facility at various occasions, we have also used this aerostat at Sagarkanya airship at the Bay of Bengal during 2018 to measure the aerosol measurements. On the right side, you can see it is also used at NPL Delhi to study the boundary layer effects. And also you can see deployment of our various aerostats at TIFR balloon facility. Coming to the crux of the topics, that is the Wi-Fi antenna testing that is made at balloon facility. So CDOT Delhi, they want to have this Wi-Fi internet facility to provide this internet facility at various locations or rural areas in the north parts of the India. So they have come up with two payloads. One is patch antenna and another is vector antenna. So initially they have tested this patch antenna. The payload weight is very small, something around 1.8 kg. And we have deployed it up to 75 meters altitude with a test range of 200 meters. Then they have used multiple patch antennas with the same aerostat. Again, they have tested this sector antenna, which the payload weight is around 6.5 kg. And they have reached an altitude of 50 meters with the test range of 200 meters. So for this 6.5 kg, we have used a 20 cubic meter aerostat, and for 1.8 kg, we have used 9.8 cubic meter aerostat. So before going to the design of medium volume aerostat, I will just explain about the material extruded, because the use of material is also important as we talk about the aerostat. So generally what we do for zero pressure balloons is like we extrude the material from the crystals. The extruded material is LLDP, that is linear low density polyethylene. We extrude different thickness of films for our requirements to come on. So some of the resins which we talk about is like Dolex and Alite and other metals as well. So traditionally what happens is like this is a single extruded layer, that is the heat is blown the material is extruded from a single air-blown material. So there, the material uniformity is not is within the range, but there is some non-uniformity as well, and the heat, some of the resins, they doesn't melt properly. So what we have done is like we have done co-extrusion of LLDPE, that is multiple heating chambers will be there, so that the material is properly heated, and it is heat blown is very good, and they are and these heat blown material is rolled into sheets. So these sheets will be used for the fabrication. So it this is also having better porosity of the material. So what happened is, like, in the meanwhile, the same Wi-Fi testing procedure is being adopted by Andhra Pradesh Telecommunications Department. They are planning to have it. So, but their payload weight comes around 35 kg. So what we have done is we have designed a 103 kg aerostat which can take this 35 kg payload to meet the requirements. So we have initially made some of the tests to develop the aerostat. One is like confidence patch. This patch needs to at least take some 100 kg payload. So we have tested it successfully, and we have made it. Then we have gone for the fin shape realization. We have fabricated and tested it. Then we have selected this LLDP co-extruded material. We have gone for the shape realization of the aerostat. The ground testing, we have done it. After after doing all these tests, we have gone for the main fabrication of the balloon. We have tested it with the inflation gas, that is hydrogen, after making the angle of attack adjustment. So the thing is that whenever there is an increase in height, there will be an increase in volume. So there must be something that which should compensate this volume. If we fully fill this aerostat, whenever it goes up, the expansion takes place. So the material may get damaged. So we need to have something like some free material that can take this volume during altitude increase. So what we have done is we have made something like deflation panels with elastic material, so that there is some loose material at the bottom of the aerostat. So whenever there is an increase in altitude, there will be elastic will be stretching, and the free material will get expanded, so that it takes the volume which is at the near bottom. So in this way we can compensate for this volume increase. So the thing is that, like, different aerostats are available at balloon facility to meet their user scientific requirements. Only minimum training is required to handle these aerostats. So we are always available to help in launch operations and in designing and fabricating these things. Then these things can be remotely launched from anywhere. Coming to applications, there are different applications of aerostats, like communications, entertainment, science and research, then disaster relief, and then government and the sectors as well. So future scope, what I am trying to do is, like, we have used this LLDP material to make the aerostat. For deployed in all weather conditions, this material should be able to take all the things like heat and during winter, during rainy season, everything. So we are in the process of doing research in this material. So we have found some materials like PU coated or nylon coated materials along with this LLDPE. So we are testing it, and if it comes okay, then it will be used for long duration testing also, because the aerostat typical loss of gas is around 1 kg per 1 day. So if we succeed in deploying these new materials for the aerostats, then it will be used for long duration tests as well. So when we talk about other materials, so we need to also think about the fabrication methodology, because LLDP generally is used brought together using heat sealing, but other materials like PU or nylon based, they may not heat seal together, or even think of mylar. So we need to have some other techniques as well for the fabrication of these things. So, thank you, sir.
Thank you, Dr. Stelen, for this very interesting work, basically. So in one way, this is a HAPS platform, correct now? So high
Yes.
platform. And apart from the scientific applications you have listed out, actually, I feel that this will be more useful for this online class during this pandemic, if we provide remote areas where these students are not having facility. So that is one of the very good societal application, which I was.
That is a nice idea, sir.
Yes, yeah. And in that case, I just wanted to know that what is the lifetime of this aerostat? Suppose once it is kept in a particular certain height.
Certain height or sir?
No. At a particular when you once it is kept, then how long it can stay in terms of months or how many months?
It depends on the payload weight, sir. Let us say if you are using 9.2 mm aerostat and we are carrying something at 1 kg payload, so it can stay up to 1 day, but it just the altitude may decrease slightly so that we can have it is a tethered balloon, so we can bring down back, we can fill some top up gas and we can again go ahead. So
yes,
that is a matter of 1 hour.
Great then, because it is a tethered and is a real control is there, so anytime you can do it. So this application, social application, will be very good for remote areas, because now this pandemic hit our kids a lot. Okay, just these suggestions. I want to hear my co-chair's comment. Over to you, Dr. Bikram Rana.
Thank you, Dr. Stalin. It's a very interesting and exciting talk. I actually just had one comment which Dr. Raghu just asked. So you said it's basically 1 day, right? If you have 1 kg of payload?
Yes, sir.
In case, like, what are the steps we need to do if we want to improve that duration or something?
It is nothing like that. It will be staying at like 1 kilometer altitude. So for 1 day, it may decrease slightly. It may come down something around 850 meters or 70 meters height.
Okay.
So if you need to keep it in the same height, then you can just top up some gas. You can just bring down it. You just give some small amount of gas. Then it may again reach 2 kilometer altitude.
So it is just a question of topping up and then leave it there for longer duration.
Yes, sir.
Okay. That's quite easy actually.
Thank you, Dr. Rana. And a very interesting part is Dr. Stalin has brought out that this rover, Chandrayaan-2 rover testing Pragyan at our URSC in the simulated terrain test facility was provided by this team, because we have to simulate 1/6 of the gravity. And this the video and actually I was also there during that time. So today only I came to know that TIFR, his group only has provided. So congratulations. And,
thank you, sir.
Yeah, thank you. And I think there is no, just let me check, there is no questions in that, and we don't have much time also to take up many questions because we are running short of time. And let's thank the speaker, Dr. Stalin Peter, for this interesting talk and very good work. Please be with us. Let us move to the next speaker, Dr. Abigail Fernandez from Amity University, Mumbai. So Dr. Abigail will be talking on the effect of microgravity on the growth of the Stevia rabaudiana callus. So pre-flight development, over to you. Dr. Stalin, you may unshare that one. Yes, yeah. Hello, Dr. Abigail. Yes. Slide is visible, but audio is not coming. So are you silent or speaking something? Hello, Dr. Fernandez. There is no audio. If you can type in the chat box, I think that will help us to identify what is the problem. Hello, team. Could you please?
We can see he has a microphone access, but his audio is not coming. He says just a moment in the chat box.
So while he is resolving the technical glitch, shall we move to the next presenter, Dr. Shreya Phadanavis from the same university, Amity University, and we'll come back to him again.
Hello.
Hello.
Hello. Yes, sir. So can you hear me? Can I start my presentation?
Who is speaking?
Sir, this is Shreya.
Okay, yeah, you please start, Shreya, because I think that Abigail is having some issues, so we'll come back to him. So let us welcome Dr. Shreya Phadanavis from the Amity University, Mumbai. Dr. Shreya will be talking on autonomous live growth experiments. 1. ALGE1 effect or microgravity on the growth of the stratospheric and the non-stratospheric bacterial microbes. Yeah, over to you, Dr. Shreya.
Is my screen visible, sir?
Yes, it is visible. Please go ahead.
Okay. Good evening, everyone. I am pleased to present our space biology research at the 21st National Space Science Symposium. The title of our study is the effect of microgravity on the growth of stratospheric and non-stratospheric bacterial isolates. Under this, I will be primarily talking about the pre-flight development of the microbial growth module, which is one of the sections in our complete biological payload named Autonomous Life Growth Experiment 1, abbreviated as ALG1. In this presentation, I will shed light on the importance of conducting research in microgravity. Then I will go on to introduce the Autonomous Life Growth Experiment 1 and the spaceflight mission sequence for the module. After this, we'll come across our main topic, that is the microbial growth module, abbreviated as MGM. Furthermore, there'll be a discussion about the objectives we have worked on till now and a brief about the methodology used in completing those objectives. We will then have a look at the results and inferences and finally conclude. Microgravity is a condition in which people or objects appear to be weightless. It is said to be zero gravity, but more accurately, it is 10 raised to the power minus 6 of acceleration due to gravity on Earth. So why is it so important to carry out biological research in microgravity? With the advancement in technology and ambitious space exploration missions in pipeline, it becomes essential that we develop facilities for sustainable space travel. As you can see in the pictures, astronauts conduct experiments on human heart cells and various plants to study the effect of microgravity on them. Future deep space and interplanetary missions can last for several months, and the astronauts should be provided with self-sustainable modules to fulfill all the basic needs till they reach their destinations. On these lines, bacteria are the simplest biological model to study and can be sent to low Earth orbit in autonomous modules to observe the effect of microgravity on its growth and biological processes. Understanding changes in bacterial behavior in space helps protect astronauts from infections during space missions. Also, various bacterial strains can be used directly or indirectly as dietary or nutrient supplements to support health and well-being of the astronauts and alleviate body atrophy. ISRO has selected the Amity Center of Excellence in Astrobiology to develop ALG1, the Autonomous Life Growth Experiment 1. It basically has two parts. First is the microbial growth module and second is the plant growth module. Today I will concentrate on the precursor biological experiments and pre-flight hardware development of the microbial growth module or MGM. Our payload ALG1 will be launched in low Earth orbit on board the PS4 orbital platform of the Polar Satellite Launch Vehicle, or abbreviated as PSLV rocket. The module is non-retrievable, that is, we are not going to get our biological samples back. After the PS4 platform stabilizes in the low Earth orbit, which is approximately at 550 kilometer altitude, it will stay in a sun-synchronous orbit around Earth for about 6 months. ISRO will receive data from our experiment and send it to the ground base at the Amity, Mumbai. After data analysis at the university, commands will be sent to ISRO, and then ISRO will be responsible for forwarding those commands to the PS4 platform. The aim of the microbial growth module is to study the effect of microgravity on the growth profile of the bacterium Pristia aryabhattai. We can notice the changes in its growth pattern in microgravity only if we know how it grows in normal gravity or 1G. First, we need to know its growth profile in 1G, and after the launch, we can easily compare it with growth in microgravity, and then say that we can observe this particular change is being observed in its growth profile. Hence, all these experiments are precursor ground control studies to support our experiments in microgravity. For this purpose, we have selected 3 different strains of the bacterium Pristia aryabhattai. Pristia aryabhattai BAW22 is a stratospheric isolate procured from National Center for Cell Sciences, Pune. And SAN PS1 and VC1 are rhizospheric soil isolates. SAN PS1 is also procured from NCCS, Pune. What I mean when I say stratospheric is that the strain was isolated from a stratospheric air sample, which was collected in a cryo chamber during the ISRO balloon experiment conducted in April 1999. The bacterial strain isolation was done in NCCS, Pune. This bacterial strain, Pristia aryabhattai BAW22, has a unique characteristic, that is UV resistance. This property can be exploited, and the bacterium can be used as a model for radiation resistance studies in future space bioscience research. Apart from microgravity, another major stress condition in space is UV radiation. Astronauts are exposed to 50 to 2000 millisieverts while on a 6-month-long duration mission, and the risk of cancer caused by ionizing radiation is well documented at 100 millisieverts and above. So figure 2. So the following biological experiments were conducted in accordance with to support our microbiology research for this experiment. Figure 2 shows the microscopic image of all the 3 bacterial strains. All the strains are rod shaped, and gram staining confirmed all of them to be gram positive. The first objective is to generate a growth curve at temperatures 28 degrees Celsius and 37 degrees Celsius. On the basis of literature survey, it was found that 28 degrees Celsius was the optimal growth temperature for the stratospheric strain Pristia aryabhattai BAW22, and 37 degrees Celsius was the optimal temperature for the rhizospheric strains VC1 and SAN PS1. In the enclosed setup of MGM, we are currently planning to only maintain one temperature. So we wanted to decide on the temperature for a simulation experiment. The second objective is to study growth curve pattern in a static anaerobic condition using only one temperature, which we will maintain in the module. The bacteria will be exposed to static anaerobic condition in the enclosed module setup, and hence we simulated these conditions using a prototype on ground. The third objective is to basically determine the changes needed to be done in the design of the module based on the results of the second objective. The first flowchart depicts the methodology used to generate growth curve plot at 28 and 37 degrees Celsius. Bacterial strains were inoculated in the liquid nutrient broth medium and incubated overnight at 28 and 37 degrees Celsius. This overnight incubated culture was then inoculated in fresh nutrient medium in sidearm flasks. Sidearm flasks are the apparatus majorly used for growth profile studies. Optical density readings were taken using a colorimeter after time intervals of 2 hours, and the wavelength was set to 610 nanometers. Once this was completed, we went ahead to plot the growth curve and optical density versus time. The second flowchart is for growth curve in static anaerobic conditions. The overall process is the same as previous. Only in the third step we have used a prototype of the design module to simulate. For both these experiments, proper controls were included and a triplicate set was used for each bacterium at each temperature. Now let's have a look at the results. Growth curve for all the 3 strains is shown in figure 5. Figure 5A is for strain BAW22, 5B for SAN PS1, and 5C is for VC1. As you can see from the plots, all the strains reached the stationary phase after 16 hours. Lag phase was observed in the case of SAN PS1 for both the temperatures and for VC1 also, but only at 28 degrees Celsius. A major takeaway from this experiment is that no significant difference was observed in growth profiles at 28 degrees Celsius as well as at 37 degrees Celsius. And when choosing a temperature for the simulation studies, we chose 28 degrees Celsius instead of 37. Although the microbial growth module will be completely insulated, we want to go ahead with a cooler temperature to ensure thermal equilibrium. To maintain 37 degrees Celsius inside the setup, a heating element needs to be accommodated, but as we are preferring to keep our design less complex, 28 degrees Celsius is our choice. Doubling time of the bacteria was also calculated. It is a time taken by a bacterial cell to divide into 2, and hence we call the bacterial growth exponential. This data will further help us in deciding various specifications of the module. Growth curve in static anaerobic conditions is a simulation experiment. Figure 6 shows anaerobic growth profiles of all the 3 strains. For the strains BAW22 and SAN PS1, the highest OD which was reached was 0.15, and for VC1 it was 0.08. This indicates that the bacteria does not grow in this condition, but actually as the bacteria grows, it has a tendency of settling down at the bottom of the tube and form clumps. SAN PS1 formed the biggest pellet out of all 3. We infer that this bacteria is non-motile and therefore does not grow throughout the nutrient medium. To take accurate colorimetry readings during growth curves, the turbidity of the medium should increase over time, and therefore settling down of the bacterium is not desirable. To curb the situation, we are finding ways to mix the bacterial pellet with the liquid medium and take accurate readings. To conclude, we have studied the growth profiles at 28 and 37 degrees Celsius, and as we observed that no significant difference was observed in their growth, we went ahead with 28 degrees Celsius for static anaerobic growth profile studies. We also conclude that to negate the clumping of bacterial cells, an agitation system needs to be engineered, and therefore a shaking mechanism is under development, and we are simultaneously carrying out wet lab experiments. This video shows the shaking mechanism simulation for microbial growth module. Thank you. Any questions?
Yeah, thank you, Dr. Shreya. It's a very good, you can say, it's very interesting because this kind of biological experiments will be first of its kind for our space missions, correct?
Yes, yes.
So yeah, because probably I think you are planning to fly in a PS4 first, or
PS4 platform, sir.
Okay. Then after that, it will go to the others, platforms. Thank you. And let us hear some valuable comments from the co-chair, Dr. Bikram Rana. Over to you, Rana.
Thank you, Shreya. This was a nice talk and about the microbacterial growth, and I think it will be very good use for the PS4 platform also to prove the technology. So I wish you a good luck for the project, and I don't have any further comments. Thanks.
Thank you, sir.
Thank you, Dr. Rana. And let us see any questions in the chat box. There is no questions. Okay, then let us thank the speaker, and probably I think such kind of experiments will set a new understanding of such kind of bacterial growth in anaerobic conditions. And you are studying the effect of the temperatures and environments on the such kind of species which you have considered, and this will lead to new opening to the subject.
Thank you.
Thank you, Dr. Shreya. Yeah, please, yeah, good luck to your team. So let us go to the next speaker, Dr. Abigail. Let us check whether your audio is available.
Hello.
Yes.
Yes, hello. Thank you so much for waiting patiently. Thank you, Shreya, for taking over. I will try sharing my screen.
Yes, it is visible. Please go ahead.
Yes, thank you so much, sir. A very good evening to all. I'm Abigail Fernandez, and I'm here to present our work done for the project MET Space Biology Experiment 1, titled Effect of Microgravity on the Growth of Stevia rebudiana callus, Pre-Flight Development. So this work was carried out at Center of Excellence in Astrobiology, MET University, Mumbai, headed by Dr. Siddharth Pandey. Yes. So as we all know, to carry out long duration outer space explorations, there is a critical need for nutritious food independent of Earth-based resources. And in this regard, scientists utilize low Earth orbit environment as well as simulated conditions to conduct several plant growth experiments to establish optimum conditions. Now we have selected Stevia rebudiana plant. This is a flowering plant belonging to Asteraceae family, and it is known for its. Further, we have selected a callus as our tissue model because it is an undifferentiated or an unorganized mass of cells, and it can regenerate the whole plant. So it is totipotent. That is, it is capable of giving rise, that is, one cell can give rise to multiple cells or multiple types of cells. So it is also sturdy, and therefore it can be explored for nutraceutical as well as pharmaceutical potential. Now the aim of this project ASBE1 is to develop a space biology experimental payload that will be launched to low Earth orbit on the ISRO PSLV PS4 orbital platform. The present experiments are intended at optimization and preliminary testing for the ground control experiments that will be run parallel with the flight experiments. Now, although we are not simulating the exact conditions of low Earth orbit, these ground experiments will help us to estimate the extent of survivability and also gauge the effects of either temperature or pressure fluctuations on the biochemical parameters that may be observed from the data which we will obtain from flight experiments. Now, the objectives of the study is to observe the effects of simulated stress condition, that is temperature and pressure, on the viability of plant callus, to study the response of the plant callus exposed to simulated stress, to analyze the callus health using optical data, to study the growth of the plant in callus in microgravity, and to compare the difference in the growth of callus between Earth gravity and microgravity. So over here, and we are working towards the development of an automated non-recoverable payload. So this entire payload is a 2 kg setup, and it is designed in a standard Eurocard dimension. It draws a total power of 5 watts. And the onboard computer collects and processes all the data from the subsystems, while RS-232 acts as the standard port for communication and power transfer between the space share platforms and the onboard computer. Now, the entire module is a hermetically sealed aluminum container, and it encloses all of the necessary components. In figure 3, we can see the callus that has been integrated inside the medium provided inside the manufactured module. So talking about the software on the module, it has multiple nodes for collecting, packetizing, and communicating the data, which ensures an autonomous operation of the system. Yes, coming to the experimental design, our experimental design was divided into 3 components. The first one was callus initiation.
Dr. Raghu, is the slides changing? On my screen, it is not changing. I'm still on the objectives.
I am, yeah, see the experimental design, slide number 6, as per my.
Oh, okay. Okay. Then it.
Yes. Okay.
Please
Thank you, sir. Yes, thank you, sir. So for the callus initiation, we have taken the stevia leaves from the stevia plant, and this stevia leaf is cut into a 1 by 1 centimeter piece and under aseptic conditions, obviously, and it has been used for the callus initiation. So this piece is known as an explant, and then under in vitro conditions, we grow this in the lab using plant tissue culture techniques. We allowed it to grow for 8 weeks and 9 weeks. The reason over here was we wanted to compare the varying differences in the biochemical parameters based on the different age groups. So after the callus was initiated, we have exposed it to stress conditions. The conditions we have standardized over here was reduced pressure and high temperature for 2 hours. And after exposure, the retrieved callus, as we can see here, was used for the biochemical analysis and imaging analysis. All the results were conducted in triplicates, and the results that we got were statistically analyzed using GraphPad Prism version 7. A 3-level significance was also considered. Yes, let's discuss the results of the biochemical test. So we have done the phytochemical assays. Now, phytochemicals are non-nutritive chemicals which are having health effects also. So we have done total phenolic content. That is, phenolics are metabolites that are generally linked to the defensive responses of the plants. And here we observed that the stressed callus showed significantly higher total phenolic content irrespective of the age. So here in figure 7a, we can see that C8 represents the 8-week-old control callus that was not exposed to any stress. Similarly, C9 is the control callus that was not given any stress. S8 and S9 were the calli that were used for the stress test. So here the total phenolic content was higher in case of the stressed callus. Now, high phenolics are due to high temperature that leads to hydrolyzing of the polysaccharides. And similar results were reported by Kaloni in 2019, where their group reported a 1.2-fold increase in the total phenolic contents of wheat bran when it was processed at a high temperature of 80 degrees Celsius. Similarly, the total flavonoid contents. So flavonoids are also important oxidizing agents, and a pattern similar to that of phenolics was observed, wherein the stressed callus showed higher flavonoid content than the control callus. Now, the structure of flavonoids consists of C-glycoside bonds as dimers and oligomers. And when there is a heat stress, these bonds form into monomers, and therefore the flavonoid content increases. Further, we check the non-enzymatic antioxidants activity, and we use the ABTS and DPPH scavenging activity that is widely used. So the IC50, which is the inhibitory concentration at which 50% of the scavenging has happened, was tested. And we can see again over here that the stressed callus showed a lower IC50. That means a higher antioxidant ability. Now, similar results have also been reported by Day and his colleagues in 2013, where the callus was exposed to a chemical stress. However, it showed similar results, that is, a higher activities. Now, these non-enzymatic activities that we have got are positively correlated to the phytochemical activities. So it is said that the antioxidant ability depends upon the phytochemicals that are present. So in case of the stressed callus, there was an increase in phytochemical activity, and thereby there was an increase in antioxidant activities. Further, okay, just to give you a brief about reactive oxygen-free radicals, they are produced in plants under adverse stress. So by reactive oxygen species, I mean they are highly reactive chemicals that are byproduct of oxygen metabolism, and they can lead to damage in the DNA, lipids, and proteins. So to analyze the enzymatic changes due to stress, the protein content was determined. So the a quantitative comparison over here showed a significant decrease in the protein content of the stress callus compared to the control callus. Here the reason could be because due to this high temperature, there must be denaturation of proteins, therefore a lower detection was found. Further, the enzymes that we checked were, these are two important enzymes involved in detoxification of these radicals, and they are superoxide dismutase, SOD, and catalase. So again, over here, there was around 2.2-fold increase in the SOD as well as catalase activity seen in the stressed callus. Now, at higher temperatures, there will be oxidative stress that rose up, and as a detoxification mechanism, the SOD activity, that is superoxide dismutase activity, increased to counteract on these reactive oxygen species. And SOD will generate hydrogen peroxide, and to scavenge this hydrogen peroxide radicals, the catalase activity also was increased. Now, although we get very valuable information out of these biochemical tests for the ground control, the payload is not recoverable. Hence, imaging is a crucial aspect, and we have used ImageJ software to retrieve color histograms as well as area density measurements of the calli, and this will give us information about the health status so that we can track the health of the callus when it is in a low Earth orbit. So the key findings here till now are that we were successful in developing a novel hardware design and a software architecture. And this was then used to check the effect of stress on the callus. And we saw an increase in the total phenolic content and the total flavonoid content, leading to a higher antioxidant activity. And this could be due to the generation of secondary metabolites. And a lower protein content was detected, which could be due to the degradation of proteins. Now, the optimization of imaging tools for the non-retrievable payload is being done. And also, we are parallelly working with microgravity conditions. That is, we are testing the module under simulated microgravity conditions. And we are aiming to integrate the payload for launch. These are our main references. We would like to express our sincere gratitude to ISRO for providing us with this opportunity. We are thankful to Space Infrastructure Program Office for their support. We would like to thank MIT University Mumbai for their financial and in-kind support. And we are also grateful to Paris Defense and Space Technologies for their technical support. Thank you.
Thank you, Dr. Abigail. This is yet another interesting experimental proposal from Amity University, back to back from Dr. Srayan and Dr. Abigail. So you have come up with very good biological experiments, one from botany and one from the zoology kind of things. So, one suggestion is, anyway, this is a very good experiment. This is not related to your work. You please continue with your work. One suggestion is, you may be knowing, you can go through that 2012 Nobel Prize of Physiology was given to scientists. Okay, they have actually demonstrated that these mature cells can be reprogrammed to become immature cells, that is pluripotent cells, and they can develop into another tissues, so the full organ kind of things. So probably I think next, both of you, Dr. Srayan and Dr. Abigail, you can think of, since you are already working on biological experiments, that is a very interesting, and that actually the 2012 Nobel Prize is the beginning of such kind of organ regenerations in space with integration of the 3D technology. So that will be very helpful to both of you.
Yes, thank you so much for mentioning, sir. We are actually working towards a proposal related to stem cells, and I think we'll be proposing it soon. Thank you so much.
Yeah, thank you. So let us hear our valuable comment from the Dr. Bikram Rana. Over to you, Dr. Bikram.
Thank you, Abigail. That was a nice talk. Just one small query since so are there like other samples currently you have used on particular plant and this cells? Can we kind of broaden that and have some diversified samples?
So we are working with 3 samples. We are working with callus tissue, we are working with carrot, and we are working with stevia. So for ASB1, we had focused on stevia. We are working with, as Shreya has already mentioned, the plant growth module also for ALG1. Right. We are working with carrot and tobacco in that case.
Okay, okay. So that will give you some broader idea about the different cells, right?
Yes, sir. Yes. Thank you so much.
Okay, thanks.
Thank you, Dr. Rana, for your valuable comments. Then I think let us thank the speaker, Dr. Abigail Fernandez, for her beautiful presentations and nice project proposals on biological experiments on PS4 and coming up with other full flight missions. So let us go to the next presenter, Dr. Santi Prabha from IAA. She will be talking on the development of the object visibility tool for the SING payload. Over to you, Dr. Santi. Dr. Santi, are you here? Audio is not coming, so can you just please speak because you are muted?
Yes, sir. Hello.
Yes, yes. Yeah, presentation is in now. Yeah, please go ahead.
This thing. Okay.
Yes, yeah. Thank you.
Okay. Is the screen visible? Like.
Yes, yes, it is visible.
Okay. Good evening, everyone. Today I am going to talk about the development of object visibility tool for the SING payload. So first, what is SING? This is a spectrograph instrument. The full form is spectrographic investigation of nebular gas. Work in the near UV range 140 to 270 nanometer, and it is developed at IIA, and it is planned to be launched about the CSS space station, and pointed away from Earth towards the sky. It is around 500 by 400 by 400 mm payload as shown in this figure. And what this presentation will show is during its orbit, we want to see where the instrument is pointing at any time, and what objects are visible in that field of view during time, and the visibility map of the sky for this instrument. So these are the specifications of the instrument. It is first a telescope, followed by a grating spectrograph, followed by an MCP detector. These diffuse objects, not point objects.
Santi, are you changing the slides? Because I don't know whether because
near UV range.
Dr. Rana, are you
slide
that
3.
changing slides?
No, I'm still that task summary.
Okay.
Yes. Now you have changed, Santi. Now we are in the specification. Yeah, slide number 3. Please go ahead.
Okay, there are some interesting lines in this region like carbon 4, nitrogen 3, and so on. And this is the First, ultraviolet be on a space station. So in this presentation, we'll see some orbital parameters. So there is the Earth and there is the celestial plane. Like most of us know these parameters, but just a recap. There will be a perigee and an apogee, the nearest point to Earth and the farthest point to Earth. It is an almost circular orbit, but it is it has a slight ellipticity, and a satellite will be at some point in its orbit, like this blue plane somewhere. So first we are given so the parameters of any line elements, and these are found for all the satellites. These are some parameters of the orbit, and they are given in two lines like this. This is an example of ISS Zarya. It is a space station. So here each parameter is a parameter of the orbit, and they are very informative. And using that on any date and time, we can calculate its position. Using the TLEs here, we can see this 130 number is the argument of perigee, which is actually this omega angle shown in this figure. Know that, but declination is like from the celestial plane upwards, and RA is the reference is vernal equinox, and from that anti-clockwise 0 to 360 it goes on. So then using the TLE, it gives the revolution per day, and we have calculated the angular velocity. Then we have, so it doesn't directly give declination and RA. Instead, it gives inclination of the orbit, and it also has given us the angular velocity. This using geometry and 3D geometry, we have worked out inclination and RA using these formulae. And we have calculated right ascension, declination, and right ascension of the ascending node. So this is nothing but the right ascension of the ascending node. Always it doesn't coincide with vernal equinox. There is some shift and other parameters like this. Then we have used these formulae and written a HTML program, and repeated the same calculations for our CSS space station. So in that the first two lines display the TLE, and then these are our calculated parameters. And if once we enter the Julian date in that website, it will give us RA and declination on that Julian date. Next, this program also calculates the exposure time. What follows next, if based on black body temperature. There are 2-3 ways to calculate the exposure time, which we'll see now. So based on these direction of viewing, we can also get maps, which is shown next. So a map is plotted here. So as the satellite goes along its orbit in one day, so this is a map of declination and right ascension, and it is converted to 8 of plot, because that is very easy to read, and many people use these to spherical. We can at live. So basically, if we load a catalog, it will, and now that we have got the area and declination like shown in the previous slide, we will put search for any objects which lie there and give us the catalog number of those objects. So here we have just used the Hipparcos catalog as an example. It is loaded in our file explorer, and it gives the result as, for example, HIP14 will lie in our side, and 00 right ascension and declination. These 5 objects will lie within that field of view. We'll calculate exposure time. So this is one method. If we model the source as a black body, and if we want desired signal to noise ratio, the time is given using this formula, and the back is given by the detector parameters, and CS is nothing but the flux from the source. No, but there is another constraint for our instrument. This can point the instrument, but in our instrument we will not be able to point it. But in so as the space station follows its orbit around the Earth, our payload is also forced to follow the same orbit. So, like I said, there is a telescope and followed by a slit, which is imaged by a. So that slit can be aligned. The two ways to align it, basically either parallel to the orbit or perpendicular to the orbit. And this slit will cover 1 degree by 0.25 arc minutes. And it is dumbbell shaped slit as shown in this image. So if the slit is aligned parallel to the direction of the orbit, we will get a certain exposure time. So that is a limitation and angular velocity, and this is the 15 is the time so based on this, we have thought that if we align the slit perpendicular to the direction of orbit, we will get a larger coverage, because as you can see, perpendicular to the orbit, if we have a larger field of view, we will also cover a larger region of space. So that is much more important to us. We want as much coverage of any possible objects as we can. So we had to decide which way we will orient it, and we will orient it with the slit perpendicular to the direction of travel. And we will and we will be able to cover around 1 degree perpendicular to the orbit that way. And thus we will input again that value again into the website here, and we can also get our signal to noise ratios. Okay, that is missing in this screenshot because there was less space here, but so this tool was developed. So developing this tool was an important part of the project. So Okay, that's it about my presentation.
Thank you, Dr. Santi. It is very short, but seems to be short. But what is happening is a lot of your effort has gone. We can see that you have developed some tools as well as the mathematical complexities while you are trying to see the object, okay, for this payload. And we understand that this is spectroscopic investigation of the nebula gas is not so simple. And the particular wavelength you are looking for is 140 to 200 nanometer. Was it correct? Because just the audio was little feeble at the time.
Hello, sir.
Dr. Santi? Yeah. No, the particular
Sir, could you
wavelength.
repeat the question?
Yes, yes. No, I was asking that your audio was intermittently, some disturbance was there. So the wavelength was 140 to 200 nanometer. Is it correct?
140 to 270 nanometers, sir.
Okay, 270 nanometer. That means the UV range, yeah?
Near UV, sir.
Okay, okay. Then no, what we are, because this is kind of these ionizations and all those things, how does it, because it is not a visible range, no? So that can you just highlight, because you might have explained, but we might have missed, because the audio was
Yeah, it is
intermittent.
not visible. It is in the near UV. So we want to see some atomic emission lines in that region.
Okay.
So carbon 4 is 154, 155.
Yeah.
So instrument is to resolve between this 154 and 155 and so on. Like so it like you can see this 3 angstrom resolution
Yes,
is
yes.
there,
Yeah, you
which will
need
resolve these nearby lines.
Exactly, because if you want to resolve what this is kind of two lines, 154, 155, you need a very fine resolution, correct. So it is good, because the 3 angstrom you're telling the spectral resolution is a very good number. So let us hear our valuable comments from the co-chair, Dr. Bikram Rana. Over to you, Rana.
Thank you, Santi, for nice talk. I think so. I just had one small query, maybe that. Do you have like when you say that you want to compare these two lines? Are those results available from other instruments? Have you, when they compare it, how does it compare with your simulations or whatever?
Compare what with our simulation, sir?
Are there other instruments available in this range that can measure these similar measurements?
Yeah, there is. There are some instruments there, like HUT is there. Alice is one of them.
Okay.
Alice is also a kind of near so UV spectrograph.
So what kind of improvements we will see over there when we have this?
So one of the so for us to resolve these lines and to cover this range, so the ranges for those instruments are slightly different.
Okay.
And
okay.
Yeah.
Okay, so this is a kind of unique range, and of course your resolution is very, very good. So I think you can do a better job there.
Yeah.
Okay, I think thanks.
So this exposure time calculation.
Yeah.
I have a similar tool to calculate where a satellite exposure time or signal to noise ratio is required. So those things this website will do. So that was this project.
Okay. Thank you.
Thank you, Dr. Rana. Thank you,
Yeah.
Santi. Then let us thank the speaker, Dr. Santi Prava, for this very
Well,
good
yeah.
You are telling something?
So we will integrate this MATLAB code also. So directly it will give the list of catalog objects there. So along with the exposure time, we'll get the catalog objects also.
Okay. So it's very useful then, the tool.
Yes.
Yeah.
Thank you.
Thanks.
Then let us thank the speaker, Dr. Sandeep Prabha, for this indigenous development. And probably she mentioned that once it is flown, this will be the first UV spectrograph on board a space station. So let us wait and for this development and see the openings in the space spectrography for this nebula gas kind of things. Then let us move to the next speaker. Next speaker is Dr. Malay Adhikari from Amity University, Kolkata, and the topic is very interesting. And this is something we all should know because this is legal visions, legal aspects of these enabling technologies. And overall, whatever developments we do, if we want to commercialize it, it has to undergo certain rules and regulations. So it is very important talk. Let us listen to Dr. Malay Adhikari. So over to you, Dr. Malay.
Good evening to all of you. Hopefully I am odd man out in this platform. Basically it is scientific platform, but why I am here? If we follow up the lectures, including the guest speaker, Dr. Sangeeta, lots of legal issues are coming up. Okay. And when we are putting all these things in commercial platform, then definitely whole system will be more hot. Okay. So from that angle, that commercialization of enabling technologies for legal exploration, it is very, very important. And another point I would like to share with all of you, that when you are enabling your technologies, whether it is 30 years back, 30 years after, so the social platform is very, very important to know. So in this background, my scheme of presentation is vision at the commencement of National Space Program, current vision of National Space Program, commercialization under different phases.
Dr. Adhikari, sorry to disturb you. You may please share the entire this one window screen instead of the application.
Okay.
Otherwise, we are not seeing the same slides.
Okay. So point
you please you please unshare it, then share the entire screen.
Just 1 minute. One minute. Is it now full screen?
No. Actually, what I was telling was that this full screen mode will not come here. What has to be done is you have to remove the PPT. Okay. So while choosing the arrow, it should come as an entire screen. Then on that one will help.
Enter screen. Just 1 minute. Sorry. Yes, I am putting it here. Are you getting properly?
No, I don't see. I don't know whether others are
or
seeing.
Maybe he
can
click that presentation button. There is a at the bottom right. There are 3 buttons, right? Just left to the zoom.
Okay.
Click that the right button.
No, F5 also will work. If you press F5 in the keyboard, it will go to the entire this one, the full screen mode.
I am putting it in full screen. 1 minute, sir. Now you are getting?
Oh.
No, I didn't see. What actually no, what I was telling is you just remove this PPT. Okay. That there is one close here. Yes. Now what happened is you come to that arrow. Open one arrow up is there, na? Open share.
Yes. Yes.
Yeah, इसमें click कीजिए.
Yes.
तो क्लिक करने के बाद एक आएगा share entire screen. और 3 ऑप्शन मिला.
Sir, that is I am getting actually. I am putting it here because I don't know why it is not happening.
I think if you go to presentation mode, I think that will work.
That is sir, I am following here. Okay. I don't know.
ठीक है. Otherwise the second slide में आइए तो.
Is it visible?
No. PPT is visible, but we are seeing on the first slide. The second slide, if you click, then only will know that.
No, I am right now in second slide.
That is what we are seeing on the first slide.
Yeah.
Okay, maybe it may take time, I think, sharing. So anyway, I just going ahead with my presentation. So
Yes.
my scheme of presentation is definitely how the National Space Program comments. Okay. After that, the current vision, and definitely the what is commercialization under different phases. And in this commercialization, there is one debate is going on: state actors versus new space actors. So it is like that, whether Mangalyaan or Sun mission or any other missions. Okay. Then next one, the legal infrastructure of government and legal vision. So with this, obviously, when the space program comments by Dr. Vikram Sarabhai, definitely there are two agendas. One is self-reliant and another is social development. Now this first point, self-reliant, this is same as it is. It is still going on, and my guess is that maybe after 50 years or 100 years, it will be more self-reliant, because our national agenda is Atmanirbhar. Then next one is commercialization. Hopefully when Dr. Sarabhai started this, definitely there was no such commercialization. Basically, he thought and planned for social development. But post Chandrayaan, hopefully, see the space commerce evolves in national platform. And here, after some time, we are getting so many non-state actors. Okay. And in this scenario, what happened? That commercialization happened gradually. And this is commercialization 1.0, 2.0, 2.5. So we cannot segregate or separate, but it is more or less like 3 phases, and definitely it may be many more phases, and in future it will increase. So if we consider that commercialization 1.0, so basically outsourcing the workload to domestic non-state actors. So what ISRO is doing? So they are outsourcing the work, definitely the small work, to some domestic or non-state actors. But here there is some problem. What is the problem? Who is the buyer? Again, the same, that is state actors. So there are some problem. So it is not so high level commercialization. Now next step comes up, commercialization 2.0. Now here increasing number of non-state actors. So when they are getting that we are getting outsourcing work, definitely the numbers are increased. And hopefully in Chandrayaan mission, for the first time, so many non-state actors, domestic actors, they joined. Now the next step, commercialization 2.5, non-state actors called as new state actors. So when their numbers are too much, so they gradually combine and they are start calling themselves new state actors, new space. Okay. Now in this new space, what is the big debate it is going on? State actors versus new space actors. Now definitely the first question is, whose priority it is to escalate commercialization? And the next question is whether the state actors will exist within new space actors or vice versa. Because there are some apprehension that if the new space actors will be increasing in number, so what will be the role of state actors? And there may be subsequent question. To cut short my presentation, I just put the principal 2 questions. But according to me, though the debate is going on, but ultimately it is the national agenda. Who is contributing more or who is majority? I think this debate has no meaning. Instead of that, ultimately we are developing the national space mission. So that will be our motto. Now, legal setup of government under commercialization. there are two aspects. Here one is institutionalization of commercialization. How it was happened, if we look back the history, it is Antrix, 1992. Now definitely 2019 onwards, it is different. New Space, NSIL, followed by Indian National Space Promotion and Operation in Space. And alongside, there are policies also. And satellite SATCOM policy 1997, remote sensing 2001, now 2011, and the draft policies in process. That is National Space Transportation Policy 2020 and Space Activities Bill. So these are in the existing domain, and definitely with the passage of time, there may be many more policies. Now here, what will be the legal vision? First of all, when a SATCOM policy was established, so maybe it was one. After that, RSDP, remote sensing data policy. Now it is other policies coming up like space transportation policy. So it is recommended like that. Definitely there will be a general policy, and under this general policy, there may be individual policies. So with the passage of time and with the market demand, the policies may be put under general policy, space policy, because at the end, these are all interrelated. We cannot say that SATCOM policy will be totally different. Maybe depending on technology, it is little bit different, but there are some common agendas. Okay. So according to me, so definitely there will be a general space policy, and under it, there may be divisions. Now, next point is the appropriate authority should set up infrastructure to attract investment from new space actors. Now, definitely people are very happy each and every year that more budgets are sanctioned by the government. But side by side, we have to remind that what happened in US. So they also started like that. After that, with the human space mission, there was accident and they stepped back. Now, definitely their state was existing, okay, but they are at the back end. Why? Because if something will happen, definitely nobody will give the responsibility and liability to the state. Okay, so private actors, maybe here new space actors, maybe at the forefront. But if we would like to bring the new space actors at the forefront, definitely we have to provide some kind of infrastructural facility. Like one of them is tax holiday plan. Okay, we can refer Isle of Man. In Isle of Man, there are so many interesting legal provisions, okay, for private actors. I think it is one and only unique one, and maybe there are one or two places. Now, next point is the government should encourage insurance companies through financial support. Space insurance, it is very much required, because if we see the space transportation policy, so this insurance thing is not clear, that if the private actors or new space actors will be interested, so who will finance them? Because what we are getting, like human space mission or deep space mission, this will be much more complex. When it will be much more complex, definitely the risk will be much more. So when risk will be much more, and if it will be planned that new space actors will join, so definitely someone have to take the finance and the insurance thing. Otherwise, the new space actor will not get any space here. Now, another point, maybe proactive space park or space export zone. So there must be some dedicated. Yes, there are some proposal, but it is in the process, I think. But we require some proactive space export zone. Okay. Now, the last point, that the enabling technology will be developed more complex or in-depth in space program. What I just now shared with you, that carries high risk. So what the government should provide, that more space to the new space actor, as in US they did, and accordingly the demand driven legal model should be framed. Thank you. Am I audible?
Yes, you are audible.
Yes.
Yeah. Thank you, Dr. Adhikari, for the very valuable talk. Basically, this is very relevant because most of the scientists and engineers, we never know what is the legal aspects of the technologies we
sir,
are.
I just to take your 1 or 2 minute time. So
Okay,
it was
okay.
basically
because we see thank you slide, so there is a confusion.
Okay.
Yeah, please go.
Basically, it was the launch of Bhuvan at NRSC auditorium. Hopefully, it is 2012 or 13. So when the who was practically holding the charge, so finishing the lecture, so one of my friend from Antrix raising this question. So you launched it, but whether you think of the creating revenue, now the speaker replied no. So that I still remember. So when people are thinking that enabling technology side by side, how it will sustain? Because if there will not be any commercial support, definitely it will not sustain. Yes, thank you, sir. I end.
Thank you, Dr. Adhikari. Because I was telling that this is a very important talk because most of the scientists and engineers, we never know what is the legal, actually the bindings or the obligations and guidelines when we develop the technology, because some of the technologies are having dual applications, as we know that. Okay, and when we commercialize, because it has to undergo certain legal proceedings. So in that respect, we must know these bindings. So in that respect, it was very valuable, even quite interesting. Only thing is that there was some, in the sense of slide, there was some problem, but we could hear and listen to you very clearly. And now let us hear some valuable comments from the co-chair, Dr. Bikram Rana. So over to you, Dr. Rana.
Thank you, Dr. Malay. I think this is one of the aspects that has been kind of overlooked, and it's for academician, it's kind of never paid emphasis or paid given attention. So, but I think what I gather from your talk is that some kind of legal aspects are quite important, but there should be some existing system, right? So, I mean, you might be suggesting some kind of change to the current system or implementing completely new system.
Yes.
That is what. So yeah, that is what basically my just a small comment that if there is some system already existing, you are suggesting some kind of changes to the system, or you want to completely overhaul the existing system.
Yes, to change something in the existing system.
Okay.
That is
okay.
my.
Okay. Okay. So that's good then. Basically, we need people like you. So thank you.
Thank you, sir.
Thank you, Dr. Rana, for that comment. And so then I think with this talk, we are coming to the end of this session B. And this also, I think along with this, we are ending the PS5 sessions altogether, the day 4 long sessions. So with this, let us take opportunity to thank all the presenters, today's presenter, as well as the other days presenters who are online, maybe in YouTube also. And before we conclude, just kindly share some comments on these sessions, Dr. Bikram Rana, because we are concluding sessions altogether.
Okay, great. Yeah, so this is the last session, correct? Yeah, so I think thank you first, Dr. Raghu. It was a very great co-sharing session with you. And I would like to thank all the speakers, including our invited speaker, Dr. Sangeeta, and all other oral presentations. It was very nice, mostly focused on humanoids, artificial intelligence, and of course, this diversified talk on the commercialization and legal issues that one should not overlook, even when developing the new technologies. So I think all the talks were very interesting, very nice. the biological experiments in the space from Amity universities, and the development of visibility tool from the Sync payload by Dr. Shanti from IIA. So all the speakers gave very interesting and nice results from their respective projects. So I would like to thank all the speakers, and I would also like to thank our chair, Dr. N. Raghu, and the LOC organizers. Thanks.
Thank you, Dr. Rana, for your valuable words and encouraging. Basically, your words will be very helpful to the speakers as well as the audience. And this feedback is important for them to carry on their activity successfully. And it was also a great pleasure and happiness to share with you in many sessions, not only today. So with this, I think we came to know each other, and we will have a long way to walk because our areas of interest are almost same.
Yes, definitely.
Yes, yeah, and we are nearby also here in Bangalore, just only 1 kilometers apart. So we basically, anytime we'll be meeting.
Sure.
Let us at the end of this session, let us thank our other coach here, our Dr. A.M. Durgarao, also, because he was also quite active and contributed a lot altogether with three of us. And this today's talk, particularly, we have 6 talks, and all are interesting, as you rightly told that it is a diversified session, and including biology, legal, then instrumentations, then robots. So all together, and balloons, which can provide Wi-Fi facility to remote areas for our internet facilities for this online classes. Okay, so then let us come to the conclusions, and I think we three are meeting tomorrow morning. Correct.
Raghu sir, I have one announcement from LOC committee.
Yeah, please go ahead.
Yeah, actually, so for tomorrow there will be no such plenary session or interdisciplinary session. So all the participants and attendees should come to the closing ceremony and outreach that link.
Yes.
I just want to mention that too.
Sure. We'll be there. I think hope the link is already shared to to all of us, correct? By LOC.
Yeah. So in the program update information page, that is there, and also we'll mail you. I mean, in every day the reminder mail, so that is also there.
Exactly. That we know that you people are very active and quick in acting the things. So then I think tomorrow we'll be meeting, and apart from that, what I was telling was we three will be meeting all sessions here to come up with some conclusions all these PS4 sessions, because we have to give some feedback to the LOC for that purpose only.
Yes, certainly. I think you can send some email and the links, and tomorrow we can.
Yes. Yeah, I'll be sending this after this. Then thank you. Nice meeting you all. So let us thank our organizing committee and then audience. So let us continue to have our interactions for the other sessions also. Yeah.
Sure.
Thank you.
Yeah.
Okay. Thank you.